All right, thanks for your kind introductions and thanks for inviting me to this webinars. My name is Jian-Xun Wang. I'm a assistant professor from University of Notre Dame, and this is my 5th year. My expertise is more on scientific machine learning, data assimilation, data-driven modeling for computational mechanics. Today, I would like to share with you some of our recent development of a differentiable hybrid neural solver or neural modeling framework for modeling or surrogate modeling of spatial temporal physics. Uh, so as we know, the computational modeling and simulation capability play an essential role in understanding, predicting, and controlling various physical processes like turbulence, heat flow, coupling, flow structure interactions. All of this exhibit complex spatial temporal phenomena. Well, traditional computational models is based on physics-derived mathematical models. Usually, those are PDEs. And we're going to use a numerical method, such as finite difference, finite element, finite volume, to solve those governing PDEs. So they have achieved a significant success in the past decades. However, in some practical scenarios, they also face some significant challenges. First, we know for many complex, very complex systems, the complete model form of the governing equations might not be fully known, either due to our incomplete understanding of the underlying physics, or maybe it's just not feasible to resolve all the physics, and we need some kind of like closure model. Second, even if the governing equations sometimes completely known, there are always like the physical parameters such as parameterized initial boundary conditions, material properties, physical coefficient, or model coefficient. They are often uncertain or unknown, limiting their predictive capabilities. And lastly, we know the conventional numerical solvers is often time consuming, and it's had a high computational cost, make it infeasible for many applications that requires a lot of model queries, such as design optimizations, inverse problems, or uncertainty quantifications. So recent advances in the AI and GPU computing, combined with the continuously growing data availabilities, have opened up the new possibilities to tackle this challenge. So in my group, we are interested in leveraging data and the GPU parallelization and computing to advance the predictive modeling for computational physics. So today I will focus on how to build data-driven surrogate model or data-driven low-fidelity solver for efficiently simulate or emulate spatial temporal physics. So we know, like in the past few years, we actually observed that there's a great interest in the community in developing the data-driven surrogate or reduced order models for emulating the spatial temporal physics using deep learning techniques. Some of them have shown some promise and some advantage compared to the traditional reduced order models or ROMs. Mesh GraphNet, as developed by DeepMind, is one of the examples showing the state-of-art performance. As you can see, the trained model can accurately predict the spatial temporal phenomena for a variety of physical systems, such as solid mechanics, flow structure interactions, aerodynamics flows, and other CFD problems. And the result looks quite impressive from those animations. However, if you check out their model structure, which is pretty straightforward and simple, essentially, what they did is just they built a message passing graph neural networks to learn the dynamic transition from current steps to the next ones in a purely data-driven manner. So once the model is trained with sufficient next step data pairs, and they can be used auto-regressively roll out and predict the spatial temporal dynamics with given initial conditions. And we call this type of model as a data-driven next step or one-step neural predictors. You really have this residual connection structures. So such a data-driven next step neural simulators can actually be seen as a first-order explicit solver whose time stepping schemes is actually learned from the data instead of being determined by the discretized governing PDEs. So similarly, no issue of this model is that the error could compound and the prediction will become unstable in the long-term predictions, in the long-term model rolling out. So for this periodic phenomena, such as cylinder flows, the common vortex can be captured very well. But you can see that the phase of the network prediction is actually wrong. The green dashed line is actually shaved compared to the reference in the long-term model rollout. And when the flow physics becomes more complex, like this vortex dynamics induced by a jet at the inlet of the channel, and you can see the prediction was initially good, and it quickly became noisy and eventually not physical at all. This is due to fast error accumulation in long-term autoregressive model rollout. And another issue of the purely data-driven model is its poor generalizability in out of the training regimes. So this is no issue for any data-driven models. When testing the model with a new boundary condition, initial condition, or new parameters like new Reynolds numbers, prediction could be sometimes very wrong. Well, so how to improve this? One direction for this particular case is we can further design better learning network structures, since the next step or one-step network formulation is not ideal for capturing the long span dynamics, and the more advanced sequence networks with the longer memories could improve the performance for sure. But we are more interested in the second strategy is because this model haven't leveraged any physics and completely based on data. So how can we leverage our prior knowledge about the physics and to design the physics integrated or physics informed learning model that is more data efficient and more generalizable for unseen and untrained scenarios? So first, let me quickly talk about, as for the learning, the network structure design, there has been extensive work in the natural language processing community. The NLP community has developed and explored a lot of advanced neural network structures for better capturing the coherence between words and sentences. And in many sequence models, such as various recurrent neural networks like LST, MGRUs, and or attention-based model like transformers has been demonstrated very successful. And especially the attention mechanism is a core of many very successful large language models such as ChatGPT. So we can for sure improve the models from the next step graph neural predictors such as this mesh graph net and to a sequence network based on the temporal attentions. And we designed a graph auto-encoding, and which is coupled with temporal attention models to better capture the dynamics in the mesh reduced latent space. And this new model have shown better performance compared to the next step baseline mesh graph net. As you can see, for the transitions and the periodic vortex shading of the cylinder flows, the transition and the periodic vortex shading of the cylinder flows can be well captured. And compared to the next step, mesh graph net predictions, where the large discrepancies still can be seen for a testing Reynolds number, as you can see as this graying dashed line, and this sequence model, more advanced sequence model, the prediction is almost identical to the CFD reference. And we so our attention-based sequence graph neural network has also been testing on a more chaotic flows. As you can see, they actually can capture the flow patterns, give different testing Reynolds number, and it performs much better than the next step baseline. However, I should admit that the robustness and accuracy of this model for the longer term rollout is still not satisfactory, because this time the flow features is more chaotic, and the long-term out of training forecasting becomes more challenging. So in the discussion above, we completely rely on the training data or data to build a purely data-driven model. However, we know we are not completely blind, and we really have some prior knowledge of the underlying physics of the system that we're trying to model. So namely, we know the governing equations represented by the PDEs to a certain extent. As I mentioned before, the governing PDEs may not be complete. I mean, the true governing PDEs may not be fully known. Some portion of the is uncertain or unknown, such as some like constitutive relations, some closure terms, or it involves complex chemical reactions, and you don't know a reliable model for that. So now the question is, how can we leverage, we call this incomplete and vague physics to enable better data-driven modeling? So this is the focus of this talk. So when we talk about physics-informed learning, one popular way nowadays is using the physics law to inform the model training process. Namely, we can penalize the violation of the physical law of constraints by imposing the residual of the governing PDEs in the loss function, which will regularize the neural network training. So this is known as a general idea of the physics-informed neural network, or PIN. A lot of the good works has been done in this directions, including our group. We also have contributed to this area. However, the PIN actually used the governing equation as soft constraint and most of the time, and leading to multiple loss terms. And one no issue is the nonlinearity introduced by the PDE laws in the optimization problems and the multi-objective optimizations, and can make this training more difficult. Moreover, as we discussed here, we are interested in modeling the complex systems. And if the governing equation do not have a complete model forms, for example, we only roughly know this process is diffusion dominant, and there might be a diffusion term, and there are some slight like convections, but we don't know the full like governing equations. So it is not possible to formulate a physics-informed loss function, and since the complete form of the PDE residual is actually not known. So in this talk, I would like to introduce a different way of integrating the physics into the data-driven deep learning models. So here, instead of using the governing equation to regularize the neural network training in a soft manner, and what we're trying to do is we try to maybe integrate the PD operators in the partial node governing equations as a part of the neural network architectures. This is actually motivated by the foundational relationship between the neural network component or neural network architectures with the differential equations. Like the neural network architecture component, what I mean is like the residual connections, recurrent network structures, convolutions, and graph message passings. And we can link them to the differential equation like OD and PDs. And this relationship has been recently actively explored in the deep learning community. So here, let me give you some examples. So we know in the architecture of the Renaud network, the residual network or ResNet, the residual connection is actually the building block, which bypass the vanishing gradient issues. So this residual connections, this network component, this network structure component, can be interpreted as the discrete approximation to an OD using the forward Euler stamp scheme. Since a residual block in the ResNet take the current state, apply transformations, and add a result back to the original state, and it mirrors the forward Euler step. Therefore, one can use the continuous ODE to define the residual connections, which has infinite number of neural network layers. So this analogy between the residual connections and ODEs has inspired the creation of a new class of the ResNet architectures known as neural ODEs. And another example is the mathematical foundation of the convolution neural networks by linking the standard convolution operators into the finite difference-based spatial PD operators on the uniform grid. So any PD operator such as diffusion, convection, gradient can be expressed as convolution operations. And those symmetric convolution kernels can be interpreted as spatial PD terms with a certain discretization. And this link can be extended to irregular domains for non-Euclidean space using the graph convolution operators and with the finite volume based spatial differentiations. And more examples about this link include the link between the recurrent neural network architectures and with the control differential equations, CDEs, or the recurrent structures with implicit schemes, and just to name a few. So here, let me recap our goal is to learn the spatial temporal physics. So if we know the complete form of the true governing equations, and we can choose to build the neural networks completely based on these PDEs, meaning those convolution kernels, residual connections, and the rest recurrent structures are completely determined by the PDE operators with specified discretization schemes. So here I propose that a numerical solver is one special instance of the neural networks. But as we mentioned above, like the true governing PDEs are sometimes only partial known, and sometimes you cannot resolve it in a computationally feasible way. So like here, we have the governing PDEs, and it has a null portion like a K or unknown portion U. The coupling between them could also be an unknown nonlinear functional or operator F. So in this case, we can actually build a hybrid model integrating the null PD as a part of the neural network architectures and make the entire model trainable as the neural network. So which offers strong flexibility to learn the unknown physics and also like discover more efficient numeric schemes from training data. So therefore, this time we redesign the sequence network, for example, like the recurrent network unit, and to form our sequence network for spatial temporal predictions. Namely, we directly encode those PD operators such as diffusion, convections, pressure gradient, in the partial null governing equations as a part of the network structure based on the relationship I just discussed in the previous slides. And the entire model is fully differentiable, allowing the holistic optimization and training. So as you can see, our differentiable physics integrated neural networks is actually encoded incomplete physics as part of the neural network architectures, which is in contrast to the PIN that regulates the neural network training. So this is just a general idea of the proposed framework, but a way of actually blending the null PDEs and trainable networks to build a hybrid differentiable neural solver could be very flexible. And here I just show you one of our design for learning the fluid dynamics. So here we build a sequence neural networks to learn the spatial temporal dynamics of the fluid flows. We first designed the next step learning unit for the sequence net. So it actually captured the transition of the state between two learning steps. To make the neural solver fast, here the delta t between t and t+1 is much larger than numerical time steps, usually like 100 times or at least 10 times. And the next step learning unit is operated on the coarse resolution. So we have a efficient neural solver. And we have three trainable convolution residual blocks corresponding to convection, diffusion, and pressure gradient. And they are connected to non-trainable conv residual block, which is completely determined by those PD operators. And the coupling of this component is actually based on the momentum equation, meaning the Navier-Stokes equations. And overall, it's a convolution residual network, and you can see it has residual conv structures, but actually the Navier-Stokes equations are integrated. So you can think this is like a solver or a neural networks, but it's actually hybrid. To enable the high-res predictions, trainable super resolution module is also combined in this unit. So before we actually move to use this PD integrated recurrent unit to build an advanced sequence network like LSTM or GRU, let's first to test the merit of integrating those PD operators by only using this learning unit to build a one-step predictors. And so then we can compare it with the previous like black box, purely data-driven one-step neural predictors. So here we use the same flow problem as I showed at the beginning. So this is a channel with a jet as inlet, and where the angle is changing over time to create a complex vortex dynamics. And the model is trained over different jet positions and Reynolds numbers. And here I'm showing you two testing samples where the jet position and the Reynolds number are different from training. So the left is a lower Reynolds number of 3,000, and right is a slightly higher Reynolds number of 10,000. And the first row is CFD reference, and middle is our PD integrated next step neural predictors. And last row is a purely data-driven black box baseline. So compared to the middle one, the neural architecture is exactly the same. The only difference is that all the conv kernels are trainable. So again, you can see the black box baseline can actually capture the dynamics at the very beginning, and then it will become noisy and noisy, and eventually become physical. And clearly showing the error accumulation. And this issue become more serious for this high Reynolds number case, as you see. And moreover, this error accumulations. So basically, however, our PD integrated models, on the contrary, are almost identical to the ground truths even after a long-term model rollout. So these figures actually show you the error propagation over the model rollout steps, and the model is evaluated over various Reynolds numbers and the jet positions in the testing set. So from the error propagation figures, we find like no matter it's in the training or testing regimes, the black box baseline predictions, this orange line, will be dominated by the error, especially when it enters the extrapolation range. While our PD integrated one has almost no error accumulation at all. And moreover, you can see the black box baseline has a large scattering, showing that the model is not robust over different testing case. But by integrating those PDs and equation structures, the error scattering remains very low, and showing that it's very robust. Okay, so the comparison of the next step neural predictors have shown the merit of integrating those governing PDs into the recurrent learning unit. And now we can use this to construct a more fancy sequence networks based on those PD integrated recurrent unit. For example, we can formulate a convolution long short-term memory network, or conv-LSTM networks, and where the governing PDs of the fluid flows are actually blended in, as I showed in the previous slides. And now the model training is based on the rollout trajectories instead of teacher forcing in the next step formulations. Therefore, it requires the gradient can be back propagated over the entire neural software, including those PD encoded PDs and also the neural networks. So therefore, the entire sequence neural solver is built using the differentiable programming JAX. So the whole program is coded in JAX, and we can leverage auto differentiations. So we can use this PD integrated conv-LSTM sequence network to learn and predict the 2D forced homogeneous isotropic turbulence. The ground truth is generated using DNS on a very fine mesh, 2040 by 2040, while all the other reduced order solvers are operating in a very low, very coarse spatial temporal resolutions, like spatial 64 by 64, 30 times downscale in each dimensions, and time step is also 32 times of the numerical time steps. So the training range is from t equals 0 to 800, and we test a model for forecasting from 800 to 1600. So the last column actually show you the result of purely Navier-Stokes solvers with small Gaussian SGS models. And you can see it has a large discrepancy compared to the reference, indicating that purely using the governing PDEs won't work in such a coarse and spatial temporal resolutions. Well, on the other hand, purely data-driven neural solvers, like the pure data-driven baselines, shows much better result, and it has some forecasting capabilities. But compared to the second column, our PD integrated neural solver, the prediction accuracy is much lower, and you can see the arrow is actually going up in the forecasting regions, and our PD integrated neural models agree with the reference very well, even at the very last steps after another 800 model rollout steps. And this can be clearly see in the error propagation plot. The green line shows the error propagation for the purely data-driven baseline, and you can see the error is climbing up quickly. And from the blue line, we can see the error accumulation can be significantly mitigated by integrating the PDEs, Navier-Stokes, into the neural network structures. So in the previous slides, I'm actually showing you the model is testing to forecast from the initial condition, which is C during the training. And now let's test the model for randomly generated initial conditions, which has not been seen in the training at all. So given a random generated new initial conditions, so you can see the third column, the purely data-driven models completely fails, and the predicted flow patterns significantly deviate from the reference in the second row, right? And it become completely different for a longer rollout length. So in contrast, our PD integrated models can accurately capture the dynamics even after 300 rollout steps. Well, the LES solver again fails at these resolutions, as most of the field features has been damped out. And the same observations can be seen in the energy spectrum comparisons. Like this time, the purely data-driven model won't work because of its poor generalizability. So this comparison shows that for the out of training scenario and conditions, by introducing the PDEs can actually improve the generalizability. So the same framework can be used to decide the differentiable hybrid neural solvers for flow structure interacting dynamics. Again, we built the physics integrated conv-LSTM network to emulate the spatiotemporal FSI phenomena. In contrast to a purely black box conv-LSTM, well, with all the black box recurrent unit, here we actually encode the FSIPD into this recurrent unit as fixed convolutions. And you can see the interaction between the fluid and structure are actually enforced using the immersed boundary method. The entire neural solver is fully vectorized, fully differentiable, and which is implemented in JAX. So it can leverage GPU computing and can be trained like a neural network. So here we showcase our model using two classic FSI problems. One is vortex-induced vibration, VIV, and another one is the flow over a flexible beam. So the ground truth is generated from the high resolution DNS simulations. Well, the pure solver is numerically solve the governing PDs for the FSI, but at a low spatial temporal resolutions. And you can see the pure PD solver fails as because of the coarse spatial temporal resolution, and all the flow features are damped out. And therefore the predicted structure vibration dynamics is completely wrong. And in contrast, our PD integrated neural solver actually operating on the same spatial temporal resolutions accurately capture the both fluid and structure dynamics and agree with the reference very well. So from this displacement trajectory comparison and displacement spectrum, we can see this purely PDE solvers indicated by the black lines are completely off. Here I also plot the result for the purely data-driven baseline, meaning everything is trainable. So this shows much better predictions since at least the magnitude of the drag can be captured. However, if you look at the comparison of the displacement, the spectrum of the displacement, you can see that large discrepancies can be seen for the purely data-driven baseline. It fails to capture all the details at different frequencies. So here I'm showing you the detailed comparison of the predicted flow field by different models. And the training windows I've got to mention is from 0 to 15, this normalized time. And all the model forecasting is from t equals to 15 to 90. As I showed, the purely PDE solver fails at the very beginning. Well, during the training range, both the purely data-driven baseline and our data-driven PD integrated neural networks agree with the reference very well, which is not surprising because we have the data within this range. And for the forecasting range, the data-driven baseline they have the predictive capabilities in this time forecasting, but they start to show some accumulated errors, and you can see this noise. And this can be seen clearly in the error propagation plot. So basically, the robustness of the purely data-driven baseline become worse for the long-term model rod. See the large scattering of this grain curves. And in contrast, our PD integrated neural solver is much more stable, and the error remains low, and for the longer model rollout steps, and the scattering is almost minimum. See this blue lines. Okay, so people may think, well, this neural network is kind of like serving as correction terms for like closure model. What if I separately train the neural network to actually learn the discrepancy of the PD solver and then embedded it back to the PD solver to correct it? And this, I call it a weakly coupled neural PD solvers. And I'm showing the result as the last column. And here, this red line. So it quickly become unstable and will quickly blow up. So the stability issue of this weakly coupled approach has also been observed in the data-driven turbulence modeling community as well. So now we want to test the trained model with the different spring stiffness, which has not been seen during training. So this is like a more challenging because it's not just forecast in time, we also extrapolate in different material properties. So this time, the purely data-driven baseline, the third column, completely fails, showing a bad generalizability over the out of training conditions. And the second column is our hybrid neural solver still can very accurately capture the dynamics and agree with the reference very well. And as we see from this arrow propagation plot, this time the arrow of the purely data-driven baseline, as shown by this green curves, green lines, is growing up quickly at the very beginning, and our hybrid neural models remain more accurate, even for the very last steps. And as for the displacement, the prediction by the purely data-driven baseline is just not stable, and it quickly simply diverges after a while. And you can see the good performance of introducing the available governing equations and into the data-driven model. So as for the second case, we can basically deliver the same message, but for the sake of time, I just skip this case, and let's move to the discussion of the cost. So the inference cost of the trained hybrid neural FSI solver for a single learning step is merely 20% of that of the numerical FSI solver on the phi grade for one numeric steps. So considering that each learning step typically covers multiple numeric time steps, so the proposed neural model offers the notable speed up for long time span predictions. And for this 2D VIV problems, we know it's not super expensive. The hybrid model can accelerate the computation by more than 8 times when simulating the same physical time length. But here I want to mention that here the purest solver on phi or coarse math, they are all GPU accelerated solvers, which is fully vectorized and running on GPUs, which is already much faster than the traditional numerical solvers like OpenFOAM on CPUs. Actually, we have done some comparison between the two solvers, but here the comparison I'm talking about is actually the speed up compared to this GPU solvers. So if the baseline is a classic open source CFD solvers on CPUs, the speed up could be much more significant. And the cost of training the neural models, usually we train on our RTX A6000 GPUs, and it's comparable to conducting a single high-fidelity FSI simulations on 8 CPUs in terms of the war times. So in the last couple of minutes, and I would like to discuss about the uncertainty quantifications aspect of this framework. Although the differentiable hybrid neural models, as described above, have shown the significant advantages over the black box neural networks, but to address the intrinsic uncertainties in these models remain a challenge and also a concern. In this model, well, integrating the domain-specific knowledge into the neural architectures, they are not immune to the uncertainty from the multiple sources. For example, in this model training process, which is formulated as a PD constraint optimizations, so the data could have the measurement noise, right? And it will introduce the data uncertainty. And when the training data is sparse, the uncertainty could arise due to the lack of data. So as we integrate this physics derived mathematical models into the neural network architectures, so the physics knowledge sometimes is not precise, 100% precise. They will introduce a model form uncertainty. And there are always physical parameters as those in the boundary conditions in the governing equations which are unknown or uncertain. It will introduce parameter uncertainties. And finally, the neural networks over parametrizations lead to a complex loss landscape and introduce many local minimum, which will also introduce the neural network model form uncertainty. So the data uncertainty belongs to aleatoric uncertainty that is due to the intrinsic randomness. While the other belongs to the epistemic uncertainty, which is due to lack of information. So here I will present a novel probabilistic version of the differentiable hybrid neural modeling framework and designed for predicting spatiotemporal physics, but with uncertainty quantification capability. I call it diff hybrid UQ. And this framework stand out due to its capability of quantifying the associated uncertainty propagations in a scalable manner. At the core of our proposed approach is the integration of a deep ensemble-based stochastic weight averaging Gaussian method and with the unscented nonlinear transformation. So it can effectively estimate and propagate multi-source uncertainty inherent to the hybrid neural models. So it offering us both robust predictions and also like comprehensive UQ capability. So to effectively quantify the inherent uncertainty associated with the predicted state variable V at time t, it is modeled as the random variables denoted as capital V. We usually use capital the capital case to represent random variables. So the probabilistic model is designed to characterize the probabilistic distribution of the state given the modeling input x tilde and training data set D. So the model input include coordinates, initial boundary conditions, and other null parameters. And the trainable neural networks and unknown physical parameters, they are collectively represented by theta, okay? And then the D represents the training data set. So the target conditional probability distributions can be obtained by marginalizing the posterior distribution of theta. And this integration can be done practically using Monte Carlo method, where the theta j is actually sampled from the posterior distribution. But now we still face three challenges to be solved. The one is how to model the likelihood functions, namely how to model the state prediction given the input x tilde and the parameter theta. And the second is how can we practically sample the posterior of theta? And the third one is how can we propagate uncertainty over the linear and nonlinear PD operators within this differentiable hybrid neural model. So let's first look at aleatoric uncertainty. To account for the aleatoric uncertainty, the measurement noise epsilon of the state is assumed to be additive Gaussian noise with zero mean. And namely, the conditional probability of the state is the Gaussian, and where the mean and diagonal covariance matrix approximated by the differentiable neural models with the trainable parameters. Alternatively put, the output of this differentiable hybrid solvers is a probability distribution of the predicted state variables and characterized by its mean and covariance, the first and second moments. So now it's not a deterministic one, actually output the distribution. And given the data set, the joint likelihood and can be computed using multivariate Gaussian density. So if we ignore the uncertainty associated with the trainable parameter theta, so the training of this differentiable hybrid model can be formulated as the minimization of the negative log likelihood. And this training process only allows the model to quantify the uncertainty arising from the data noise, since all the trainable parameters only have a point MLE or MAP estimate. So to truly assess the total uncertainty, we need the parameter posterior. However, we know to directly compute the posterior using the traditional Bayesian sampling techniques like MCMC is infeasible due to the extremely high dimensional parameter space, like theta space. Usually you have a million parameters for deep neural networks. So this will slow the convergence and require extensive computations. And additionally, like we know, the deep learning or deep neural network often present a complex posterior landscape that traditional Bayesian methods struggle to navigate. So here we actually integrate the use of a deep ensemble method and with the stochastic weight averaging Gaussian method, the SWAG, to approximate the posterior. The idea is, as shown in this figure, the posterior landscape of deep learning models sometimes could be, sometimes is often very complex and multi-model, like this orange curve showing here. As we know that we use the stochastic gradient descent to train any neural networks, right? So the stochastic gradient trajectories with the constant learning rate, usually it contains the local geometry information of the posterior landscape. So therefore, one SGD trajectories can be used, I mean, all this SGD iterates can be used to approximate the local posteriors by fitting a Gaussian distribution like this. And here we combine the deep ensemble ideas, and we can train an ensemble of the hybrid neural models and with different initializations. Therefore, we can generate multiple SGD trajectories, and it can lead to multiple Gaussian approximation of different local posterior geometries. Okay, so this can be nicely coupled with the Bayesian model averaging idea. So we weighted this local Gaussian approximation and actually give us a Gaussian mixture model. And it can approximate the complex full posterior distributions like this. And compared to the expensive sequence MCMC sampling, this approach is very scalable and parallelizable. So now our probabilistic differentiable hybrid neural models is shown in the schematics. As you can see, to make it short, and compared to the deterministic versions, the input and output of the recurrent unit is a probabilistic distributions instead of deterministic state predictions. So typically, one of the primary metric to express uncertainty is variance, right? The often used to define the credibility or confidence intervals. So that involves how to propagate the first and second moments of the posterior distributions within the differentiable neural models, and which contains linear and nonlinear numerical PD operators and neural network and neural operators. So for the linear operators, we know the mean and variance can be analytically propagated through the phi transformation. This is quite trivial. But for nonlinear operators, the linearization actually can introduce large errors, especially when the nonlinearity is strong. So you can, of course, use Monte Carlo method, and it's going to be costly because it involves tons of samples. So here we choose to use unsanded transformations, which only need a few sigma points, which is way more efficient. So lastly, let me quickly show you a few examples to evaluate the UQ capability of the proposed method. So we first evaluated on the 2D Hamiltonian systems, and which is actually an ODE system. The hybrid neural solver is constructed by considering the right-hand side of first ODE as the neural operator. And the hybrid model is trained with the data showing in the last figures, which were perturbed with some measurement noise. And you can see the noise level are different for different variables. And this difference in the data uncertainty can be successfully captured by our diff hybrid UQ model. And also the epistemic uncertainty is also reasonably estimated since it grows in the extrapolation region without any training data. And finally, you can see our UQ result are compared with the Hamiltonian Monte Carlo, the HMC, which can be seen as golden standard. It shows our UQ is reasonably good, although it's slightly overestimated epistemic uncertainty compared to the HMC result. And the second case we tested on spatiotemporal PDEs, 2D reaction diffusion equations. And it's important to know, like the train data is only for V2, and there's no data for V1. So the result reveal a strong correlation between the spatial arrows of the spatial prediction arrows in the third row and the quantified uncertainty in the fourth row for the state predictions for both variables. And to make it more clear, in this figure, the uncertainty propagation over time on 3 selected locations are plotted. And the quantified uncertainty accurately reflect the data uncertainty. And the aleatoric uncertainty become higher for the region where data is not available. And furthermore, the uncertainty increases over time, aligning with the autoregressive nature of the model as the confidence decrease with each subsequent time step predictions. So this two case shows that our UQ framework can reasonably quantify the uncertainty of our hybrid differentiable neural models. And in the last minutes, I would like to show you a more realistic case, which is from our collaboration with Honeywell. So the goal here is model the manufacturing process of carbon-carbon composites, where the chemical vapor infiltration process is the most important steps in Honeywell's recipe. So the underlying physics of the CVI process is very complex. It involves fluid dynamics, molecule heat transfer, carbon decomposition and diffusion, and both homogeneous and heterogeneous reaction that involves hundreds of species. So our understanding of such a complex system is way from complete, and our purely physics-based modeling is not feasible. And on the other hand, some observation data can be obtained from Honeywell during their manufacturing process. However, this data are very limited, indirect, and contain a lot of noise. For example, the data available are just the weights of the sample. So now we can utilize this sparse, noisy, indirect measurement, and coupled with some limited knowledge about the underlying physics of the system to build a predictive model. So to address this challenge, we will use our probabilistic physics integrated neural differentiable model to build data-driven neural solvers with UQ capabilities. So to this end, the major foundational physics should be distilled based on a set of assumptions to streamline the modeling process. Specifically, the flow outside of the preform is considered to have no influence to the diffusion process, and the flow within the preform is assumed to be negligible, suggesting that the transportation of the precursor gas is predominant through the diffusion. And more importantly, instead of simulating the multiple species and aggregate representations used, introduce effective species responsible for both diffusion and deposition process. So the foundational physics is substantially reduced to 2 PDEs, one for reaction diffusion and another one for deposition. And the effective diffusion coefficient fields, which is spatiotemporal functions, and the effective deposition rate, which is another spatiotemporal functions, and are modeled as the 2 neural operators as a function of the porosity field, temperature, and pressure field. So this model is only trained with limited weights data. So first, I'll show you like the test using the synthetic data. So the data we got is actually weights of the sample over time. So basically, we cook the sample in the oven for a while, and then we take it out and measure the weight and put it back to the oven. And so then you can collect the weights over time, those blue points. So those are all the measurement training data we have. So once the model is trained with this weights data, and of course, it has noise, and it can be used to predict the dynamics of the hidden physics, such as effective diffusion coefficient fields, effective deposition field, because they are all spatial-temporal functions. So here we only plot the dynamics of 2 locations. One is at the center, one is at a corner. The green one is center location, red one is corner location. And you can see the model prediction, the solid line, agree with the reference reasonably well, which indicated by dashed line, for both effective diffusion coefficient and deposition rate, as well as the molarity and the porosity field. Okay. Also, the uncertainty of the prediction can be quantified. Because this is like a neural network, so our neural software can be trained on different operating conditions, and then it can be used to evaluate on sea operating conditions like different partial pressures and temperatures. So those blue points, dots, shows the training conditions, parameters at a different temperature and different like partial pressures of the reaction gas. So within the red box, those are prediction on sea operating conditions, which is in the interpolation region. And you can see the prediction are quite accurate, and also the uncertainty is lower. And outside this red box are the prediction on sea operating condition in the extrapolation regions, and the prediction are slightly less accurate, but the uncertainty also increase. And the ground truths are always bounded by the confidence intervals. So for the synthetic case, we have the ground truths for the hidden physics. And now I'm showing you the model training and prediction with the real experiment data. So the different colors shows different operating conditions, and that different, which is the different partial pressures of the reacting gas. And the top two figures are the dots are the weight data used for training, and you can see the uncertainty is pretty low for the training case, but it increased for the region that where the data is missing. And once the model is trained, and we can test the model over different operating conditions. So the two figures on the bottom are testing scenarios, where the experiment data, those dots, are only used for validation. We don't use them for training. And you can see our model prediction are reasonably good, and for different partial pressures, and especially like when testing the test the model with the partial pressure, which is more like interpolations, like this 30 kPa and 15 kPa, the uncertainty is low and it's more accurate. And well, when testing the partial pressure, which is more like extrapolation, like the 100 kPa, which is out of the training, it's way out of the training, and you can see that the uncertainty is actually large, but it's still like the confidence interval bound the experiment data. So this is all I want to share today. I think it's a little bit over time, so I will stop here, and I'm happy to take any questions. Thank you.
Yeah, thank you for the presentation, Professor Wang. That's very detailed and very cogent, and your slides are great. All right, I think we do have a couple of questions that I'm going to open up in the chat right now. And the first one is Abhijit Joshi asks, can we know a reference paper for the PDE-based neural network structure or a GitHub for that architecture that you mentioned, if possible?
Yeah, sure. So we have two papers. One is still under review, but I already have that on the archive, and we have another paper. I think recently it will be out. So we're gonna share all the code and for different structures on my lab GitHub page. I think we haven't finished because the paper is still under review, so we haven't released the code for the latest result I show, but definitely all of them will be shared through my GitHub page.
Okay, I think you're talking about the PPNN paper and archive, right? So I think I have the link to that, so I can share that on the event
sure.
Slack.
I have another one for the flow structure interactions, and I think that paper is also on the archive. And the code will be available soon. I will ask my student to, put the code together and share it.
Okay. The follow-up question that is, can the models that you show predict physics such as Rayleigh instabilities or boundary layer interactions?
So we haven't tested like the boundary layer. So you mean like the turbulence boundary layer interactions?
Yeah, Abhishek, you probably have to clarify that, but I assume so.
Yeah, so actually this is ongoing things we're doing. So I have my ONR project is for like modeling the wall bounded flows, wall bound turbulence, and especially with the irregular roughness patterns. And now we have developing this differentiable solvers and for that particular purpose. And we're going to release that solver as well, and which is fully differentiable and which is built on based on the Jack CFD, but now we make it make it 3D and it can handle the boundary layers, and we verify it using the other DNS solvers. And so yeah, this is underway, but we haven't tackle very challenge like 3D turbulence boundary layers at this point. But I think that is the goal, and I'm also interested.
Yeah, I think this follows up to the next question by Agel as well. Agel asks whether the proposed frameworks that you have in this presentation have been tested on complex fluid flow cases, for example, particles in a carrier fluid, or with non-periodic boundary conditions, like you mentioned with the wall-bounded flows, I guess.
Yeah, we definitely have tested on the non-periodic boundary conditions, and we have inlet outlet boundary conditions, pressure-driven boundary conditions. But we haven't do any particle-driven, like particle laden flows at this point. But I think this is a pretty general like framework that yeah, but I just don't have the bandwidth to tackle every different problems. But I think yeah, it can be done.
Yeah, Agel, I will also post the FSI paper in the general discussions later. That probably has a lot of non-periodic boundary conditions. So Daniel Mohades asks, I am interested in your perspective. How do you view the academic and industrial landscape in terms of adopting differentiable plus data plus physics solvers? Do you see this happening imminently, 5 years longer, or 5 years or longer?
That's a great question. I think people now are interested in the differentiable physics and also like the how to leverage GPU to accelerate the computations. And you can see most existing legacy solvers they are still like implement using like C+ or Fortran. And now like some I know some groups they are focusing on like developing the next generation solvers, and even like Cascade they have spent a lot of effort to develop their GPU solvers. So, I think this going to be a trend for both academia and industry. I know Google is invest money and to develop the like the solver that can leverage GPU parallelizations. And to be honest, I can even from our own group, we have the small scale GPUs, and we only have like we test our 3D turbulent channel flows using our solver on the 1 GPUs. So the mesh, I think the mesh size was like 6 or 7 millions, and to run that for one flow through time on our 1 GPU, A6000, it only takes like 1 hours. But if you do the same resolution on the open form, it's going to take like 50 hours. So the speed up is very I think it's very exciting. And if we can also blend in the trainable neural networks and to speed up, I think this is very interesting field. But you can see this is still like not a very this is intrusive, so that involved the software development. So so practically, I believe like most industry, they will still rely on the existing more mature solvers, and they I think for practical use, this is not. I don't think it can happen in next year or next few years because I think for let the industry to actually adopt this, this field has to be developed to a more mature stage, and yeah, definitely need more effort. That's my perspective.
Okay, Pushan Sharma asks a pretty long question, so I'm gonna Pushan, can you unmute and ask Professor Jian-Xun Wang your question?
Yeah, sure, I can ask that. So I had a question regarding the error propagation plot that you were showing, where the black box model error increases due to error accumulation, but the PPNN or the that error remains almost constant. But I was wondering if those errors are some statistical velocity, like mean RMS, or the instantaneous velocity profiles. I'm asking because usually in a high turbulent flow, if there is a small error even at the first time step, that should change the profile, the instantaneous velocity profiles completely, right, in the following steps. But yeah, so that's the question. So is it the instantaneous profiles that you are comparing, or the statistics?
Yeah, that's a good question. First, I want to clarify that the example I'm showing is not turbulence, so it's just unsteady flow. So we compare the MSE loss, which is for the instantaneous flows. But I agree with you, for the turbulence flows, we don't have to like match the instantaneous flows. We just want to match like the filtered or averaged flow statistics instead of like matching the each instantaneous flow. So for like that's when we move to like the turbulence case, that we need to redesign the loss function and rely on like a time averaged or at least the moving window averaged statistics to define the loss function. That makes sense?
Yes, that makes sense. So you're saying we should change the loss function during training when we have highly turbulent flow?
Yeah.
Okay, I see. Okay, thank you.